Alright, looks like we are live on the C++ London Uni. If I can get it to update. Yeah, here we go. Okay, I'm going to dare to load this. Hopefully I can mute it quick enough. Oh, yeah, there we go. Okay, cool. So let's just let everyone know, because there's probably nobody watching right now. I'm doing an impromptu, and learn to spell. Impromptu. I hope you can enjoy the sound of my keyboard. I love mechanical keyboards. You probably don't though. You can of course watch afterwards if you're asleep. And with that, I have fulfilled the Wadsworth constant. If you skip the initial part of the video, you skip the crap. Right, so first of all, we just want to give out a shout out to John Edwards, really, for this. He attended our Thursday workshop today, and he'd taken on a little task, which essentially consists of simulating a 10-pin bowling game. So the idea is that you need to represent the rules, the basic rules of 10-pin bowling. So of course, you have a turn, you take a turn, you have a frame, obviously, which is X number of goes. I can't remember how many it is. I'm going to be looking at the game rules as I go along. And then obviously you have to compute a score as you go along, and then part of what makes this an interesting task actually is that you potentially don't know what the current score is, or may never know the score. If the player constantly gets strikes, then it's computed at the end, and additionally they also get an extra go on the final turn. So we're gonna do C++ 17 for this, and we're gonna call it bowling game. I did actually do some of the code with John, but that was on my Mac. I'm doing this on my PC, so I think it's probably better for everyone anyway. If we just do it, from scratch anyway. So you'll get to enjoy me sort of theorizing about how to do this as we go along. Okay, so we've got our CMake lists now. We've got our bowling simulator. I'm going to try and make the font bigger, hopefully. Let's see. Right, before I do any code, I'm going to get some essentials. So the first thing I'm going to need is, of course, Catch 2, the framework for unit testing, because we're going to do this TDD style. And hopefully this will sort of give you an idea for why TDD is so powerful. So I'm going to download catch.hpp right there. So you can't see this, I've got another screen open, I'm just downloading it from GitHub right now. And then we're going to grab this, cut that, and let's go to my CLion projects, which is here. And I've got Justin in the background being the peanut gallery. What? I could make the CMake list do that, but I think to keep this relatively simple, we're just going to copy it in. Right, so catch.hpp is shown up. So the first thing I want, obviously, is to have a separate main executable, and then I want to have an implementation. So let's just organize this bit nicely. So we're going to have a few folders. Let's have an include folder for my headers. I'm not going to bother using that yet. We're going to have a source folder for my translation units. And then we're going to have a test folder for my test translation units as well. And then obviously what we want is we're going to move main into source because that's the entry point. We'll just let it do that. Give it a sec. Okay. And then of course we now need a main for test. So we'll just make a source file, call it test main. Don't even need that, does it for me? Test main.cpp. Don't add that to a target. Let's just do that. And now I'm going to add that as a new executable. So we'll call it bowling. Let's go test bowling simulator. Test bowling simulator. And that's test/test main.cpp. So now we've got our main executable, which will eventually run the simulations when we get there, and test bowling simulator, which will actually just execute unit tests. So let's just have an auto reload here. And then what I'm going to need to do is move this into... I don't really want to move it into include, because even though it's a header, it is part of the tests. So I'm going to stick it in test, because it's not an include for the main source code, and therefore no one should care about it in the main include folder. Right, so we've now got that. So we've got our test main.cpp, and we'll just use this with catches. How helpful macro for getting a main. So what is it? Define catch. Oh, I can't even remember. So we Google catch define main, catch 2 even. So I have this earlier. Let's see. Catch config main. There we go. Quick Google gives you what you need. Config main and include catch.hpp. Cool. Okay, so that's now given us a main. So hopefully I can tell it to execute this, and it should compile. Hopefully. And run and do absolutely nothing, in theory. I've got Visual Studio updating in the background apparently, so it's probably not going to help with the build speed, but tell you what, we won't wait on that for now. Let's just crack on. We're going to make our first source file. So the biggest part of TDD is to sort of think about your problem and break it down into the sort of simplest unit you can, because obviously TDD also involves unit testing. So if we think about it at the top level, right, we're going to have our overall sort of simulation of the game. Underneath that, obviously, you're going to have a frame. Underneath that, you're going to have a turn. And then a turn obviously consists of some pins. You've got 10 bowling pins, of course. And you know you're going to knock them down. So we probably want, first of all, a representation for the pins. So we can have something where we can tell it, you know, okay, knock down this pin. We can tell it, tell me which pins are knocked down. Probably should also not necessarily let you knock down a pin twice. There should maybe be some safety checks, but I'm going to go for the minimal approach. And because we're doing it TDD, we don't write more code than we need. So first of all, let's just create our test file. So we'll call it, let's say, test pin set.cpp. So we'll add that to the test executable, and hopefully it will do it. Cool. So there we go. It says no test ran. That's excellent. We've got started. Right. So one thing I like to do when I'm actually working on this kind of thing is to do my implementation in the same file as the tests, and only when it gets large enough do I actually split it out. So we'll just start. We'll include our catch.hpp again, and now we're going to start a scenario. So scenario. What's the most simple sort of thing you would expect from a pin set? So let's say that when you first construct one, when you default construct one, i.e. you make an instance with no arguments, then all of the pins are standing. So default constructed pin set has all pins standing. Okay. So given a default constructed pin set class, and then we'll have pin set pins. When we ask check if all the pins are set, auto all pins set equals pins dot then the value or result, let's say, should be true. Okay, so this is fairly trivial, right? So we can now say require all pins set. Okay. Well, obviously this is essentially a failing test already. This isn't even going to compile because I haven't made a pin set class at all. So let's start out by doing that. So we'll have class pin set, and then, well, at the moment all we strictly require to satisfy this test is a function called all pins set. So we're going to do that. So let's have a public function called bool all pins set const return true. In fact, technically this const is too much because this doesn't require const. So we're going to pretend that I was more responsible and I made a const instance. So now it is required. So again, you never write more code than you need when you're doing TDD. And this is the extreme version. Obviously, when you know what you're doing, you don't really take such baby steps. But I'm doing this to sort of demonstrate how you evolve your design by using this methodology, and I'm taking baby steps deliberately here. Okay, so we've now got one test, and it's obviously going to pass, right? So let's just run it, and hopefully it won't be too slow. Because if it is, I'm going to have to crack on again. No, it's linking already. That's good. I don't know if it's using MingGW, because Jonathan was also complaining that the linker time on Windows was horribly slow for reasons that are not obvious. No, okay, there we go. All tests pass, one assertion, one test case. So we've got a fairly useless class here. So what we do though is we now evolve that. So new scenario to force us to generalize. So scenario default, no, not default. Let's say a pin set with one pin knocked down does not return true when we check all pins are standing. It's nearly over the 80. That's over the 80 column limit there, but whatever. Okay, so given a default constructed pin set class, when we actually make one first. I can't use const this time. Let's say pin set pins when we mark a pin as knocked down. Pins dot knockdown. Let's call it knockdown pin. And now I'm sort of getting into design now, because I need to decide what I'm going to represent a pin by. Because obviously that's internal to the class, but I still need to pass it something. So I could just use a number. Could just use 1. But then I'm probably going to have to store this in an array, and I might end up with an off by 1 error. So I'm going to pretend we have an enum. So we'll call it pin : 1. And we'll implement that in a second. Then all pins set should return false. And obviously I'm just going to use it directly here. Require pins.all pins set equals false. And I do hate that it tells me I can simplify this. You could obviously just use an exclamation mark, but I think this is more idiomatic and readable. Why would I want to reduce it to 1 character? Yes, it's shorter, but it's
require underscore false.
Is there a require false?
Yep.
Oh, there is a require false. Even better. Okay. All right. Thanks to Justin. There we go. We'll require false instead. Okay. I like that. Nice. So the first thing obviously is to make it compile. So I'm going to declare my enum now. We're going to use an enum class, of course. Strict typing. Pin. And obviously we're gonna start from, it'll be 0 base. So we'll say 1, which is automatically 0. If you want to be explicit, you can do 1 equals 0, but that looks a bit weird. So we'll just leave it with just 1. So 2, 3, 4, 5, 6. And part of the reason for this design decision is that it's 10-pin bowling. We're never going to try and scale this to 10 pins. Sorry, to like 100 pins or 1,000 pins. So this is reasonable, because this is as part of the design. This is not going to grow. It should not grow. So you can also see that these are currently unused, and strictly speaking, I could omit these if I wanted to really go crazy and only add them as I go with the tests. But I think that's pointless. We gain nothing doing that. So we're just gonna have those 1, 2, 3, 4, 5, 6, 7, 8, 10. Okay. So we've now got that. Well, we need our knockdown pin to be implemented in order for it to compile. So let's have a void knockdown pin p, we'll call it, and we'll make it do absolutely sod all. So we've got that. We can now run it. I think I might have to change compiler if this linking takes too long. I'm becoming slightly concerned how long this takes just to link the damn thing, which I'm not entirely sure what it actually uses to compile it. Let's have a look. Project settings, where is it? Is this project settings? Tool chain. Yeah, it's using MinGW. It's a bit slow. They should really add support for Clang. I literally have native Clang. I don't know why they make you do this, but okay, we'll soldier on for now. So we've got a failing test. I don't know why it's not in color. That's a bit of a shame. Maybe I can force that somehow. But okay, so far we had the scenario, and obviously it didn't pass. Well, okay, we needed to return false here, and we needed to return true here. So I can't just make it return false. That would break it. We need to generalize someone now. So that means we need a representation for our, well, potentially need a representation for our pins, right? So let's see what would be. I think a stood bit set is probably a good way of representing these pins. It will scale nicely. So I'm going to include. I can spell include bit set. Okay, so now we've got the bit set class. So now I need a field for it. So I'll have stood bit set. And of course it's 10 pins. Right. So now of course I need to tell it to knock down a particular pin, right? So obviously we can say pins and then static cast in a_t, for example. I haven't need to include something more for that. Let's just separate that. C headers on their own. C stood int. We'll static cast our enum class to an 8-bit int, and we'll set it to, of course, false, so that then clears the pin. And then we can generalize this now, so I can just do return pins dot all, I believe it is. Okay, and then if this is correct now, this should implement what we need. And of course, this one should still pass. It should not break this test, and it should pass this test. So let's see what we get. Maybe we have a bug because we didn't check what stood bit set defaults to. This is why unit testing is so valuable. You'll see that we'll have discovered that we made a huge mistake, or not necessarily a huge mistake, but a fairly silly mistake. So, and oh dear, well, what have we done? We've actually made the new test pass. So this one is now passing, and the old one is now failing. I'm going to try and scale it. Sorry, I forgot to scale this up, so hopefully you can zoom in on it at home. But I'm going to. How do I get into presentation mode? Is it F11? Is it F11? Let's try F11. It's not it. View. Here we go. Enter presentation mode. Right. That's actually horrible for me to develop, but probably better for you to read. Okay. So we broke this first test. Why did we break the first test? Well, it's because if you default construct a bit set, then they're all actually set to false. So what we in fact need now is a constructor in order to fix this. So let's go with a constructor. So of course it needs to be public. So we'll do a pin set. Or actually, no, we don't need a constructor. You know what? This is you can initialize it right here. So I'm going to say 0b 1 2 3 4 5 6 7 8 9 10. So that's all 10 bits set to 1. You could obviously represent it with a decimal, or you could represent it with a hexadecimal, octal, whatever floats your boat. But I think this makes the most sense. And since we're using C++17, I'm going to use the lovely decimal separator. Actually, well, what's the best way to separate these? 2? Maybe we'll do them in 2s. Yeah, let's do them in 2s instead. That's more readable. So it's 2, 4, 6, 8, 10. So it's a bit easier to read. It's exactly the same. Right. So now, in theory, if I run it, and I don't know if the presentation mode lets you see the output though. Can I? Oh, it does. Okay, that's not bad. Not bad at all. So when it eventually builds, we'll hopefully see that it's going to work. This is slow, really. And unfortunately, there is now. Oh no, it's recovered. Okay. It's building. All right. So while that happens, let's crack on. So scenario. Pin set with a pin knocked down. Can confirm that the pin is not set, but all others are. Right. So, given a default constructed pin set pass, when we mark pin knocked down, pin. Let's do 4. Why not? Then and they passed, as you can see. The pin should be considered knocked down. So pin. Oh, it's knocked down pin, isn't it? Sorry. Probably should just call it knockdown, because I mean, what else are you going to knock down? Pins dot is require pins dot. Should we go for is knocked down or is up? Is down? Yeah, let's go for is down. Require pins dot is down pin 4. And then all the other pins should be up. The problem is I've knocked down pin 4. It's a bit annoying to go over it, and well, I suppose I can get away with this somewhat since we're in range. So we'll say that for 0. Well, no, that's not. We can convert, can't we? There's not a nice way to represent this. I think I'm gonna be explicit. Let's just be explicit. Require pins dot is. Actually, let's use the same function just because we don't want to introduce too much change at once. Pins dot is down 1. What if we OR them? Actually, we can do is down 1, 2, 3. Nah, it's just 2 ones per line. So, can I duplicate this line in C Lion? Is there a way to do that? Let's just copy paste. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A little bit verbose, but I'll go with it. Of course, copy pasting is a bit of a risk, but usually if you break something, if the test is wrong, then you'll know, because the code, it's rare to make the code incorrect in such a way that it still passes the test. It's not impossible, but it does happen. 1, 2, 3, 4, 5, 6, 7, 8, 9. I've already got too many sync. So that's a fairly obvious bug. Cool. Okay. So we're going to expect that that one's true and the rest are all false. All right. So we're then going to go back to our implementation up here and have a bool. And you know, just to make this a little bit better, let's make the pin set pins mutable, and then let's do pins mutable here, and we're going to just do const auto ref pins equals pin mutable. So we can even ensure const correctness as we go. So we need the is down. So let's go ahead and do that. So bool is down pin. Oh, come on, don't freeze on me. p const and return false. So now we should, in theory, fail this test. So we're going to run it. Hopefully it'll at least compile. And I don't know why the linker is so slow, it's awful. Let's just shrink that down a bit, get a bit more screen space. Okay. Alright, so I know it's going to fail because I just returned false, and then that means this is obviously not going to be true, and sure enough we have test passing except this one. The pin set, with pin knockdown compared to pin not set. Okay, we need to fix that, don't we? So obviously let's we have to generalize already, so we know that we've successfully set the pin to false here. So in theory I should be able to fix this by just saying return pins dot test and then static cast uint_t. And there is an argument you could make here that I should not use an enum class, because then I wouldn't need to perform the static cast. It would obviously just work as a number. But I think this probably, I would argue that it's better to suffer that somewhat in your implementation here, so that anyone consuming it has that type safety. I mean, obviously someone can be silly and they can static cast a number to a pin type, but they've got no incentive to do so. So, okay, so we've done that. Hopefully, if I run it, is there a shortcut for this? What's the run? No, there we go. Shift F10. Okay, so we'll do that next time. So now if we run this, it should, should work, right? I also obviously didn't need the require false. I could have done like is down, or I could do a bitwise or here. And obviously, if any of them were true, it would still fail. But I think this is just for simplicity. We'll make it this verbose. So, yep. Oh no, I've made a mistake. Pin dot is down 4 is still false. What have I done? Oh, we've got our first bug, and the test is caught it. So let's see how I made this awful mistake. So we require that this is true, and in my code, I test if it's this return. So let's see if this is down, it gets set to 0. We then return false. So the problem here is that the logic is in fact inverted. This would be correct if it is up, but it's in fact is down. So obviously we can just do return not pins.test, and now we should be returning the correct. I've forgotten the key, the shortcut already. Shift F10. Right. So now just a simple logic error there, but we caught it already. So now this should pass. And it's still not passing. So let's see, failed, expansion not true. What did I do wrong? Oh, someone's got a call. So, I still have a bug. So this is why unit testing is so great. You realise where you mess things up. So what's wrong? Everything else is passing, but this is not. So we know that we've done something wrong. We're calling knockdown pin. We take a const reference to the object. So okay, let's see what knockdown pin's doing. Did I forget something there? So we have element. Oh, is this because of UB? So we will cast the object to a uint. We'll set it to false. So that's going to be pin 4. You index it by the same one. Is it because I'm introducing UB into the program? No, it's not. I've obviously got a bug in my test. So this is correct. And this is what I was getting at, is that you can usually have a bug in your code or a bug in your test, but very rarely do it in a way that you'll cause it to pass. So you can see here that we expect it to be down here. It can't be down and up. So the code is now correct, but this obviously should not be here. So we will just delete that line. No, not move it, delete it. Thanks, sea lion. Right. There we go. and we've corrected the test now instead of the code. Let's do our shortcut, and this should now of course work because we are not expecting Schrodinger's pin. Okay, so we've now built that successfully. Let's have another scenario. So I think we can do a fairly simple one for checking if it's up. So let's see, scenario is up, returns the opposite of is down for any given pin. So given a default constructed pin set, when we knock a couple pins down, so we'll say pins mutable dot knock down pin, let's say 7, pin 9, then the pins up should not match, should be the opposite of pins down. Oh, sorry, is down. So let's just change that. And let's just make our pins mutable, and obviously require pins dot is. Let's do a sanity check first, actually. So require pins dot is down pin 7. So we still require it's down. Require pins dot is down. And there isn't actually a point I would make here as well, is that technically speaking now, because I'm calling these in sequence, I could do something really insidious, and I could make is down return something different if I call it a second time. Also, that should be 9, of course. I can make it return something different if called a second time, which I wouldn't catch if I cached the value in a variable. So instead of caching it in a variable, I'm going to actually call it repeatedly. So if the value it returned ever did change somehow due to weird behavior, it would then fail this test. So then of course we do require pins dot is down pin 7 doesn't equal pins dot is up pin 7. So we now require that is down 7 is different from pins dot is up, and of course pins dot is down pin 9 doesn't equal pins dot is up pin 9. Okay, and that's a fairly reasonable test there. Okay, so we're just checking 7 and 9. We could also just check when we haven't knocked down. I mean, there's no reason not to, right? So we can do require pins dot is down pin 4. Okay, so that's fairly reasonable. Of course, we need to implement it. So let's implement it. So bool is up, pin p const. And of course, you always want a failing test before you make it pass. You should always make sure that the test you've written is failing, because otherwise you don't know if the test itself is correct. If you write a test and it just works straight away, then either you've gone and implemented it before you even validated that it wasn't doing the required functionality, or something's wrong with your test. There is such a thing as testing for confidence, which of course is when you add tests that are just expected to pass. But you should generally avoid trying to test for confidence until you've kind of got a fully fledged application, and then you can sort of throw more on there. That's more really a kind of QA thing. But anyway, so we've got our failure. It's not doing what we want, which of course is what we expect. False, of course, does not equal. Oh, sorry, false does equal false, so it fails that check. Looks a bit confusing there, but false is equal to false. So let's fix it. So of course, the simplest solution here, of course, is to just call is down and negate the code. So return not is down p, and of course that should pass our test now. So okay, already we've now got something that can essentially service everything we need. I have something that when I construct it, it will have all the pins standing, just like in a real game. I have something that I can ask it if all the pins are set. I can tell it to knock down a pin. You can check if a pin is knocked down. Probably another useful thing is you might get a strike. So I probably want to know if all pins are down as well. And in fact, considering that, we currently have is down and is up, and this is probably not a great name. So let's rename this to all pins up. And of course, we can just do a refactor here because this is fairly harmless. It's not going to compile. Fine, I've messed it up. There is a refactor feature in C Line, which I should have really used when I just did this, but it's only a couple of places. Okay, so that should still compile. So we'll just let that run. And so we'll just implement an all pins down now as well. So let's make the scenario. So scenario. Let's say all pins down returns true when we knock down all the pins, given a default constructed pin set. So when we knock down all the pins, and I'm gonna use a loop for this. This is again, I'm using an enum class. This is slightly ugly, but I don't want to write too much code, so I'm just gonna demo this. So for auto I equals static. I'm just gonna use static cast to make it somewhat correct. So use uint a t pin 1. Actually, no, we don't even need. No. Let's. Can I increment? You know what? We're about to discover something that C++ may or may not let me do. I is less than or equal to pin 10. Increment I. Can I increment an enum? I'm not sure that's valid. Yeah. So the problem is that I can't actually do it. So we're gonna use static cast. So static cast uint t pin 1. And this is already getting a little bit ugly, really. But uint a t. You could probably write. You should probably write a wrapper to clean this up. But we're gonna start with this. The idea is just to make sure it works. But yeah, this is somewhat ugly. Okay. So then we're going to call pins mutable dot knockdown pin static cast pin I, and we're done. I'm going to get rid of the curly braces because I personally don't really bother with them when it's a one-liner, but not necessarily saying you shouldn't. They are considered fairly good form, but that's a fairly ugly for loop there, to be perfectly honest. But you know, it's doing the job. So we've knocked them all down. Then all the pins should be considered should be down. So let's just get our usual const auto ref pin equals pins mutable. So okay, this is a reference, a const reference to this object, an alias of pins mutable. So require pins all pins down, and just because we want to actually require false, pins up. Okay. So obviously this is not going to compile. I could just run it. That's technically a failure still, but I know that's not going to compile, so we can just crack on. And let's implement that then. So bool all pins down const. Now we're just going to break it. So here we go. You know, let's just make it interesting. Let's return true. See what happens. This is where I've obviously broken it through this. This will satisfy the. Sorry, this will satisfy it, but this will hopefully violate it. Well, no, it won't. In fact, so now I've written a passing test, and I haven't in fact implemented it properly. So let's just run it and make sure I'm correct. Yep, that's a cause for concern right there. I did not expect to have a passing test, because I shouldn't have a passing test. You should fail first. So I've done something wrong. So what did I do? Well, I made it. It just so happens it returns true. So now I have to ask myself, well, is it because my testing is in some way lacking? So what can I do to make the testing do more? Do I need to adjust the test? Well, I could have it validate all the existing functionality, but that's not really going to help me. So I could make it say that, well, you should expect this to be false first. So that's which is not a bad idea. So we can make a failing test by doing that. So to fit it into this though, there's kind of two schools of thought, which is that one, I could make a different. I could copy and paste this scenario. And strictly speaking, yes, you should do it. You know, I'm just gonna do it. We're gonna make a new scenario. And we're gonna copy it. We're gonna make it fail. So all pins down returns false, and we leave all pins alone. So we knock down. Do nothing. Should be up. So I now need to change that to false, that should be true. Okay, and now we've created a failing test. Yeah, okay, cool, so that's failed. Of course, I can now satisfy this test. So this requires this to be false, so I can switch it. Return false, cool, lovely, brilliant. Of course, now we've ensured the robustness, because the function's returning false, which means it's gonna. I've made it pass the test I pasted above the previous one. Or the last one, but now I'm going to make that one fail. So there we go. We've expanded the testing, and we've now ensured that we still don't have passing. So this originally was passing because I happened to return true, and I said to myself, well, okay, clearly I'm insufficient somewhere, because it should not pass straight away. It's expected to fail. So I introduced a new test that required the opposite. So now I have a problem, because it can't be false for this one, and then true for this one by any kind of decisions. It's forced me to generalize, so I'm going to generalize. So of course, again, the simple solution to solve it is to simply return not all pins up. And this is actually going to kind of demonstrate something. This was deliberate, but this is not correct. and I think you can probably realise why that's not correct, which is kind of why I did it deliberately. So it's going to pass, but we have a bit of a problem here because we've actually sort of violated the assertion. Because if I knock down one pin, that doesn't mean all the pins are down, does it? So this is where you kind of have to think about your design. So we're going to add another test, and we're going to use that to validate what I just said. So scenario, all pins down returns false when only one pin is down. And I'm just going to copy paste most of this. When we knock down a pin, and of course I don't need to mess around with this anymore, we can just do a simple little knockdown pin. Pin 5, let's do 5. Then of course we should require that all pins down is false. Not to be considered down. So all pins down should be false, and all pins up should also be false because they're not all down and they're not all up. So hopefully now this should be a failing test. The key thing to remember here, though, is you've got to really think about your design while you're doing TDD. It's not going to magically just give you flawless code just because you've written a test thing in it. But that's the part of TDD is it doesn't guarantee everything is going to work, but it does mean that you have something to build on. So imagine that somehow I didn't think about this and I shipped it as is, and then someone came and was like, well, it told me that I got a strike and I only knocked down one pin. Well, that's obviously not good, but I've already got this corpus of tests here that validated everything else was not a bug, and I've already had a few bugs while developing this, so at least I got rid of several already. I can now just add I just add a new test. Okay, life, that's life, right? You can't guarantee everything, but add a new test, and then you've prevented that problem ever happening again because you've got the body of test. You can keep on building on it. So anyway, I've done my test. I've now got a failing test. So my bug came in. I was like, oh no, what's wrong? Oh, this is what's wrong. Write the test that verifies my bug. So this test is one I've introduced. It's that captured the bug, and now of course we're gonna fix it. So, well, what have we got to do? So we need to know if they're all down. But the inverse of this doesn't apply, right? This made sense. It's the opposite. If it's not up, it's down. So sorry for this one. If it isn't down, it must be up. But this isn't obviously true. Well, what we can do, obviously, we should go into our pins and do a comparison. So let's see what methods this has, and it's listing all of the internal ones. That's not really what I want. So let's just have a quick look on CPP reference for stud bit set. And I know you can't see this, but if you want, go to search for stud bit set, go to cppreference.com. And in the documentation, we have checked if all, any, or none of the bits are set to true. So we want none in this case. So pins.all, pins.none. Okay, and of course we don't want the not. If I'd have forgotten that, it would have still failed the test. So that's good. So now it should be correct. And when it eventually links, we'll know. Come on. All right. So while we wait for that, let's crack on. So let's think about what we've got, and there we go. We now have passing code. I want to know if all the pins are up. Potentially, I'm not sure. I'm not entirely sure if I will actually need that. I do want to know if all the pins are down. Convenient way of knowing if there's a strike. I want to be able to tell it to knock down a pin. I may want to know if a particular pin is down. I may want to know if a pin is up. I probably more likely want to know how many pins are down realistically and how many pins are up potentially. So let's add that as a test. So let's say scenario when pins up return. Did we use that yet? Did I? Pins up, pins down. Nope, didn't. So let's do that. So pins up returns let's say 8 when we knock down 2 pins, given default constructed pin set when we knock down 2 pins, 2 pins. Down pin, let's say 8. Then let's take the old const auto and again. Then pins up should return 8. And of course require pins up equals 8. Cool. So obviously not compile, so we'll do our usual thing, right? So let's make it compile. So I'm going to use a uint8t. Let's use fast8t. So just for anyone wondering what fast8t actually means, it means that it will be a minimum of 8 bits, but it may use a larger value depending on what is essentially fastest for that particular platform. So you have a guaranteed minimum width of 8 bits, but it could be larger. Obviously, you should not use it as if it was larger. Don't put larger numbers into it. That's undefined behavior. But it's just for it's an optimization essentially. So we've got our uint fast8t. Want to know how many are up. I'm using unsigned, of course, because it should never be a negative number. And let's see, pins up, const, and let's just return 0. It should fail, hopefully. And if we go to this code here, so it's starting to get a bit large. So I'm reaching the point where I'm thinking I will move this into a translation unit, because initially it's convenient for your development because you can just use the same file, and of course you have the tests there. So when you refactor it, when you move, cut and paste it, you have a fairly low risk of introducing a bug because you'll just fail the tests after you've refactored. So okay, so we're still failing. We require that pins up is 8, and of course 0 is not 8. So let's make it pass. And if I wanted to be extreme, which is what I was talking about earlier, I would just return 8 and I'd make the test pass, and then I'd add another test sets, 3 of them. But we're gonna speed up a little bit now. So instead of doing that, we're going to generalize already. And again, if you do generalize and then you find that something's going wrong, slow down again. But I think we're somewhat safe to speed up, I hope. Maybe it'll come back to bite me. We'll see. But okay, so we need to know how many pins are up. So if we go to our lovely standard library, we can see that there is actually a count function. So nothing can really go wrong here. This is fairly safe. So we can call pins.count, and stood bit set will actually just give us the count pins that are up. So let's do an F10, and hopefully that will work. And while it's doing that, I want to test if pins down returns the inverse count. So I could make a new scenario, but I'm going to extend this one. So pins down should return 2. So require pins down equals 2. Grand total of 10, 8 plus 2. And of course, even though you've modified the test, should still fail first. So we're going to return 0 there. And as long as that fails, we can move on. I know it's going to fail, obviously. 0 is not equal to 2, so we'll just assume that it's already linked and run. And of course, we need the inverse. If we go back to our standard library documentation, There is the count, which tells you how many bits are set to true, but there's not one that tells you how many are actually set to false. There is a size, tells you how many it can hold. There is a count, really. Peanut gallery. So obviously we can do that. I mean, there's different ways you could do it. You could iterate over it. You could iterate over it and check all the unset ones, but that's silly. It's way less efficient. So we're gonna go for the obvious option, and we're gonna say pins dot size minus count. And again, if I'd have accidentally done pins dot count minus pins dot size, we would have failed the test and we would have caught that. So in theory, this should now pass the test. Step 8 and 2, and hopefully we will find that it's correct. Oh, right. Oh, we broke something. Right, see. So pins up should return 8, and pins down should return 2. Well, pins up actually is returning 2. What have I done? What have I done? I modified the wrong function. And this is why unit testing is great, because we modified the wrong function. Just put that back there. We know that because we broke the test. So now I've done it correctly, it will actually pass. And as you can see, it is indeed passing. Okay, so we fixed all that. So I think we've pretty much sort of squeezed pretty much everything we can get out of this pin set. I mean, I know it will tell me how many are up, how many are down. I can knock pins down. I'm not going to implement a member function for putting them up, because quite frankly, you don't put pins back up. When you play bowls, they all get reset. You don't just put them all up. So no, I don't need a reset function because I'll just instantiate a new version of the class. There's no reason to reset it. So once I want to go back to a state of all the pins up, I just throw away the existing pin set and take a new one. So it doesn't require me to have a pointer. You can just replace it. It's copy constructible or copy assignable, even though I'll reset it. Right. So the next thing we want then is to sort of refactor this, and so we are going to start doing that. If I can make this thing display what I need, so I need project, and we're going to make a header. Does it let you refactor classes? Let's see. Refactor, move, extract. No, that's not what I want. Let's try move. Will that do it? Move deck. No, that's not what I want at all. So let's just do that ourselves. So I'm going to put this into a header file, and we're going to put it on not on the test. It'll be actually on both. It's going to be on both. So we're going to call it inset.h. And as much as I love header guards, I'm tempted to change this to pragmal once. Actually, I'll allow it. I'll allow it for now. And so we're going to test pin set, and we're just going to cut and paste this, and cut, and that's gone. So then we've got our header, and it's obviously not going to compile because the stuff that needs is missing. So include space there, and bit set. That's what we need. We need CSTD int. I could have just cut that, but there's only a couple of them. We need our enum, of course. So again, it's not going to compile because the enum is missing. So at this point, I could make the enum a member. I could make the enum a member of this class potentially. I could also put it in its own header. But I think that it's useless on its own. Its purpose is really to service pin sets. So I'm just going to stick it in line with this class. So we're going to go back to test pin set. I'm going to extract this, stick it in stick it in with the other. I don't need this anymore. And so we'll just paste that in there. And there we go, we've got our header, we've got all our types. That should, in theory, work. I just need to include it from here, so let's include it. And hopefully it will. No, it won't work because I need to edit my CMake lists because I've now started refactoring. So we're going to do target include directories test bowling simulator. Set to include as private, not public. And there we go. Now I should find it just fine. So we've got hopefully a application that still compiles, although we're not quite done yet. And just see that for yourself. It's building. It says it's linking, then it's good, because we know that we haven't actually separated the translation unit yet. So hopefully that will actually work. There we go. So it's linking, and it must work. Okay, so we're not done though. We need to actually separate it properly. So we're going to have a source file. I could do a class, but I'm going to do that my way. So inset.cpp. No, I don't even need that. It does it for you. We'll add it to the targets. Okay, and now let's do our code. Include inset.h. And now we're going to extract our methods. Let's see if I can do this side by side somehow. I don't think that's a feature. Move, extract, variable constant method. No, I'm not. Maybe there is, but generate. Nope. Okay, so I'm just going to DIY it. Which is a bit annoying. Let's try it on refactor. Move. Move members to class. I don't want to. No, that's not what I want. Extract. Okay, nope, so I give up. Alright, so we're going to have all pins up. And I'm just going to copy the whole thing. Reduce it to a semicolon. And then we're going to go over to pin set. And of course, we're going to paste that in there. Pin set, all pins up. Const all. Why is it not working? So close that. Okay, excellent. So we've now got all pins up. And it's rinse and repeat, really. So we've got this one. Cut it down. I think there is a way to do this in C-line. I'm probably missing it. But essentially, we'll go through it. It's not that many to do. In fact, let's just speed this up. Copy the whole lot, first of all. And then 1, 2, 3, 4, and 5. Okay, let's paste it here. Copy this part. 1, 2, 3, 4, and 5. Okay. What are you doing? Right. Okay. So now the translation unit's there. I need to fix the CMake list, or it's still not going to compile. Or it may have done it for me. Oh, it's done it for me. That's nice. So it's actually, well, actually I told it to. I've forgotten about it. So there we go. Excellent. Okay. Let's go ahead and compile this. Does it work? Hopefully it will. Yeah, it's linking already. That's good. So now we've got it refactored. So now we just have the tests in this file. This is purely the tests. Okay. So we have our pin set, and the next thing we need now, of course, is probably to represent a turn. You know, a single turn. So you take a turn, and in that turn you get to bowl once or twice, depending on whether or not you get a strike. So obviously, if you knock all 10 pins down the first time, that's it, and that turn has ended. So originally when John brought this to me, he was saying that you don't have to cater for multiple players. You sort of simulate one guy playing on his own. I think we'll start with that, but we'll try and design it in a way that we can sort of hopefully scale it out into a kind of game controller and make the pieces reusable. So obviously the next thing I need obviously is a sort of a turn. So what's that? I don't like the word turn on its own though. So we'll test play turn. Yeah. I'll call it player turn. A player's turn. That makes more idiomatic sense, doesn't it? So we've added it to our test only. As usual, we're going to include. Oh, I can't see it. There we go. Catch.hpp. Okay, and then let's have a scenario. So scenario. What's the most basic thing we need to think about? What's the most essential piece you need to turn to it to do? I need to tell it. Well, I probably need to tell it that I've knocked down some pins, or maybe it should manage it itself. Technically, this class could, in theory, run a kind of simulation, but it's not really a game controller. It's representing the state of a turn. So you should be able to put it in a given state, and you should not be able to violate the validity of a turn. So what's the simplest case we can think of? Probably just a strike, right? A strike is one turn. It will know the turn is over. So let's say scenario, getting a strike on the first turn, or first bowl results in turn ended. Given a default constructed instance of a player turn, when and this is the thing, I could give it a command to say knock down everything at once, but I'm not sure I want to. I think I'll have to tell it individual pins. It would make more sense, right? You bowl, and you don't just say knock down everything. You have to give it individual pins, even if it's all 10 of them. So when we knock down all the pins, and then the question here is, how do we want to do it? We should obviously use the enum. But is that a really convenient state? Because now we're having to sort of repeat ourselves potentially. Although it's annoying for testing, it might make more sense later because you do have to represent like this pin, and that it was knocked down. So, or perhaps you give it a pin. Perhaps you can just give it a pin set. So maybe that makes more sense. So it'll have one pin set state, and it can then transition in the second one. But then that's potentially problematic. We might need to implement operator overloading back in pin set in order to sort of do that. But then maybe that's a good way to do it. We probably want to interface it away though, because I need to be able to mock that. So now we're getting into sort of bigger design decisions. And I'm sort of sitting here, not even typing code, just thinking it through. I think we are going to use the pin set type. I do think it makes sense. Your simulation will take a pin set object. It will then knock down some pins, and it will give the turn object the state that it's in. So what we can do is it'll start out with them all set. It can take care of that itself. Well, and again, this is where it's getting more complex. Do we want to knock it down? And again, this is obviously just a trivial, silly game. The point is to treat this like it's something that's going to be maintained. This is completely contrived, but in order to learn, the point is to treat it serious manner. So we want to knock them down. We want to interface it away. Who's going to have ownership? You want to encapsulate it properly. Well, yeah, if we use the pin set, what's the caveats there, right? So if it's interfaced away, it can't instantiate it. You'd have to construct it with an implementation of the interface, but it's probably reasonable actually. So I can construct it with an implementation that has all the pins set, and potentially actually I could reuse it then. I could construct it with one that doesn't have all the pins set, and then I need to pass it, on the first after the first turn, an instance that is in an instance of pins that's whatever state it should be, and it will essentially knock them down, or not knock them down, but the implementation of the pin set interface will do a comparison and unset pins. Potentially it could, if I want, throw an exception if I end up turning pins up. But yeah, I think we're going to go for this design. So we're going to have we need a pin set then. So when we don't knock down pins, when we pass a pin set with all the pins knocked down. So pin set pins, and where's the helpful? Here we go. I'll enter. Lovely. I don't know why it's using angle brackets. That's part of my project. Generally speaking, you should use angle brackets for external stuff, which actually is why I should use that, and quotes for internal stuff. So we have our fake player turn. We have our turn to knock down. Is it knock down pins or knock down pin? Did I actually name that? No, I called it knock down pin. That's fine. So knock down pin. Actually, no, I want to interface this. This is already inconvenient, so we'll say mock pin set. I pin set. So now I'm being forced to interface things away. And also, this might be the point where I discover the joys of trompe-l'oeil. We'll see. So I'm going to make an interface. So let's make a new folder for these. So interface. We're going to have an I pin set now. I pin set, and it's just gonna virtualize pretty much all of this stuff. So we're just gonna copy this, and we're gonna paste it into the interface, and we're gonna call it I pin set, and it doesn't need any of this stuff anymore. But it does need to know about the pin type still. That's a concrete enum type, so we're going to actually cut that out to the interface, which means we're going to include the interface here. So include the interface, keep the folder names to be explicit, and we have to put it there unless I change CMake, so that's obviously enforced. And now we can paste it in here. So we've got our enum class. We don't actually have anything else going on. There's a few things you need to do here, and this is why I encourage using sanitizers. Actually, address sanitizer would catch it. Unit test. If I was to run my unit test with address sanitizer, it would catch that I currently don't have a virtual destructor in here, but I'm going to put one in because I know I need to. And of course, need to make this virtual. So we're going to just set these all to virtual. Do a quick copy paste. So these are now virtual. I did need C TDD in, however, so let's just plug that in there, and we can remove it from pin set. That's fine. I'm not sure I like the look of that. It looks like it says IP in set, which is kind of confusing. I'm going to live with it for now, but that's slightly unfortunate. Equals 0. Let's just do a quick copy and paste, 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 paste. Cool. And of course, the all-important virtual I set default. So there we go. We've got our interface, and I'm going to pop over here, and we're going to inherit from it. So public I pin set, and ta-da! We've got an implementation. Now I just need to actually ensure that I didn't screw anything up. So let's just copy the space as well. No, not that. and mark it override, mark it override. The override keyword is actually just a safety check. It doesn't make it override. It would be an override anyway. It's just a safety check in C++11. Excellent. So we've now interfaced it away, so I can go back to my test player, turn over here, and I don't even have a class yet, but we'll make our mock. We need a mock for this, so I'm going to implement mock here, and this is where I probably will need trompe-l'oeil for this. I'm gonna try and sort of hack it together, but it's probably not going to scale for me. So let's see. Let's just use a struct since it's a mock. Mock pin set. And let's not include the interface now. Don't need the implementation. And yeah, I'm already regretting this concept. Let's grab trompe-l'oeil. Let's see. C++ trompe-l'oeil. Header only C++ 14 mocking framework. That's the one. It's header only. Excellent. Okay, this is just what I need. Except it comes as a zip or a tar GZ, which is a bit weird for a header only, isn't it? Surely this is backed out failed experiment. I'm not sure what to make of that. 143 kilobytes of that looks like a file right there. All right, let's grab it. So grab the zip file because Windows does not really go well with tar GZ. Okay, it's literally just the entire GitHub repo, and you can't see me doing it, but I'm just going to dump it in the test folder. So I've never used trompe-l'oeil, so it's going to be an experience for both of us. Okay, so what does it say? Obviously we need to include it. That's usually a good start, isn't it? Right, okay, well I've included it. That's a good start. Okay, this looks fairly similar to Google Mock, actually. Why does it make me put override? Okay, whatever. Alright, so apparently the syntax for this thing is as so. Make mock. Well, actually, no, I need to have these to hand. Right, let's see if I can split the view. Can I split the code view? View code. This isn't very useful, is it? Structure. Surely there's a way to split the view. Can I not? Let's try it. Can I just put it? Yeah, I can just ruin everything. That is not very helpful. Fine, I'll just copy them and do it that way. So we've got these. Pop over here. I'm just going to paste it as a function, right? It's not really very helpful, but fine. Okay, so we call make const mock 0 because it doesn't take any arguments. And then it seems to be that you do the name followed by the function's type. So it's a bool that takes no arguments. I don't think we need the const somehow, and you can put override if you like that kind of thing. I mean, I suppose it makes sense because you could technically mock something and have a concrete implementation. So I suppose if it is concrete, it makes perfect sense. Right, so let's just do the rest. So make const mock 0. Oh, come on, don't freeze on me. Things down. Bool. Override. This is actually not looking too bad. And then we've got one that takes an argument. So was it make mock 1 knock down pin? It's actually kind of figuring it out as we go. Void pin override. And yeah, okay. Let's try and copy this bit, speed things up. So I've got a const one. So let's just copy this over there. Call it is down. Actually, it takes one argument, and it's in. We're good. Okay, and then we can just copy that now for the next one. Is up. So we get the case right, and that does the same thing. Make, what is this one? Is this const? Yeah, const. mock 0 pins up uint at nothing override, and then we'll just do pins down by copying it. Okay, and that looks like a pretty decent mock. So we've got our interface, which has the virtual methods, and we've got the struct here, which of course is the mock. So we're going to give it a shot, and hopefully we can use it. The question is, how do I dispatch? Require call, forbid call, require call. Okay, this is fairly simple. Excellent. Okay. So when we have a turn, I need the mock now. So let's instantiate one. So mock pin set mock pins, and we're going to say maybe knockdown pins not a good name. Say mark knocked down. What's a meaningful name for this that would not be confusing? So I don't want to use a bad name because it'll just be horribly confusing later on. It's bad for maintenance. I'm not saying you necessarily need to spend ages of it, and part of the reason I'm spending ages is because it's 10-pin bowling, and a lot of the words you use for this don't really lend themselves to being particularly meaningful. But we need to describe what we're doing, don't we? So we're going to let's say knockdown from pin set. We'll pass it mock pins. Okay. So we've got that. Then, well, what's the state? Let's try first of all, turn ended. Then turn ended should be true. Okay. So turn. Actually, let's be good. Turn mutable. And then we'll do const auto ref turn mutable. Require turn dot turn ended. Well, our test's not quite complete because I didn't set the mock. So we shall say it will need to check. Well, it will need to check if all pins down is true, right? I mean, that's basically what we're saying here. So we can set that up. So require call. You pass it the mock, so mock pins. This is trompe-l'oeil now, and we're expecting it to call all pins down and dot return true. So we give it the mock, and it's required to call all pins down, and when it does, this will return yes, all pins are down. And then of course we expect turn ended. So we've now got our mock. We don't actually have a class though, so let's make the class. So class, and you can see how TDD does force you to design, because as I was doing this, I was like, oh no, I need to interface this away now because I need to validate that it's doing the correct thing with the implementation. So now this is completely segregated, and it was forced. So well, I say forced on me. I had to think about it because I'm doing TDD. So we have our class player turn, and we obviously need to have a knockdown from pin set function. So void knockdown from pin set by pin set ref, and we can make this const. Actually, we don't need to worry about it being mutable. Pin set, and of course it needs to fail, so I'm going to make it do nothing for now. And then of course we need to implement our turn ended. So we will just have turn ended const turn false. So this does nothing, and this is false. So we should, in theory, end up with this failing and this failing. So we'll give that a shot. And as you can see, we're already getting a bit more advanced. Oh no. Oh no, don't tell me, don't do that. Are you telling me that trompe-l'oeil doesn't actually work? Error? Oh Christ. Alright, so yeah, I'm unfortunately gonna have to inform you that I know how to fix this, so I'm gonna do it. You shouldn't really have to do this. This is a bit rubbish. It may not be trompe-l'oeil's fault, or it may be trompe-l'oeil's fault, I can't really tell you. But my guess is it is. It depends, I'm not sure what compiler I'm actually using these days. What is it, CMake, or C-build? It doesn't bloody tell me. It might just be GCC standard library that's behaving, so I'm not going to jump to blaming it. What does it detect? Let's have a look at the configuration. Settings, MinGW, 7.0 is GCC. It's GCC. Alright, so hopefully it's detecting GCC. Yeah, it is. No, in fact, this is showing me it is. It's GCC for sure. But I don't see where it's including anything. Okay, we're gonna do a ugly hack and hash include mutex. Please work. Please work. No, I am busted. Do I just not have recursive mutex? It slightly concerns me that that's using recursive mutex. Apparently, maybe this just doesn't work on MinGW, which would actually suck. But we may be busted. Let's have a look if this has any recursive mutex. Oh dear. We don't have gthreads because we're on Windows, so we are actually out of luck. Not to worry. I don't blame trompe-l'oeil then. I do, however, need to undo the mess I just made in it. Let's get rid of that. And we're going to switch to the wonderful MSVC compiler, which I'm sure will not bring us any kind of trouble on top of the problems I'm already having. So MSVC, I'm going to switch to Studio. Hopefully it can find the damn thing. Great, the support is experimental. That already fills me with confidence. Apparently there's an x86 AMD 64, whatever the heck that is. I don't care about that. The version 8.1, whatever, I don't care. Hopefully this will work. It's detecting the compiler. That's not really. I want to use Clang, but I don't see. That's okay. It's detected it. Let's just let that go. All right. Let's see what we get. Shift of 10. Probably go from being out of compile to being completely broken. Nope, it's still building with MinGW. How about we make it not do that? Can I not change this, please? No? Come on, there's got to be a way to change this. Settings. Where is the project setting? Tools, no. Welcome to the learning curve is switching compilers in CLion. It's fun. What if I double click it? No, that's that. Ah, there we go. Okay. I've set it to the default. Maybe that's going to make a difference. Or it's going to completely ignore me probably. Because I suspect that if CMake has already cached the build. Oh, there we are. Oh, here we go. Maybe this is actually going to work. Oh, yeah, we're getting somewhere. Yeah, it's getting better. Ah, we have success. We actually do. Okay, cool. It actually links quicker as well. I don't see it running though. It's not very good. Oh no, it does run. Excellent. Abort has been called. Just ignore. Oh yeah, that's MSVC. It's now going to spit that up because if you fail a test in catch, it essentially throws an exception and you stood terminate or you abort. Yeah, I know. It's an assert. Right, so as you can see, we have our failure though that we expected, despite the annoying dialog box. And turn.turn_ended didn't do what it was supposed to do. The question is though, I don't see what trompe-l'oeil did. This obviously should have. Maybe it's probably not catch, it's probably this. So we require a call, and the behavior of trompe-l'oeil apparently is to just abort the program, not give me anything useful. Surely it's doing something more useful than just vomiting up a failure when it runs. Let's just run it again. I just want to see that run. No, don't build it again. It's already built. Press retry to debug application. Yeah, that's not going to work, is it? Yeah. Okay. Apparently trompe-l'oeil's just going to kill you. Okay, so well, a failure is a failure nonetheless. So we know this is broken. So let's just fix that by doing the most silly thing possible and return true. And then we're going to run that. Let it recompile. And we'll get to find out if the cause is, yeah, it's trompe-l'oeil. Okay, so we can make this pass obviously in the most sort of daft way possible now. I can just do pin set dot all pins down, and if I can spell it correctly, this should pass despite being completely useless and not actually solving anything at all. And sure enough, it does. It's exactly what we expected. Yeah, sadly, I'm not very impressed by that from trompe-l'oeil. If you use Google Mark, it gives you value, like nice output on the console to say like, oh, this mock wasn't satisfied or this wasn't satisfied. It doesn't just kill the program in an unceremonious and not particularly useful way. It's a bit of a shame, really. Anyway, we'll soldier on with it. So I've got all pins down. But this isn't very useful. Now, obviously, again, I could add another test to make sure it's going to, validate it. But I don't think I'm going to take it down those baby steps anymore. So we'll generalize a little bit. Otherwise, we'll spend forever doing this. So obviously, this needs to check if all the pins are down. And then it needs to obviously set if the turn is ended. So we'll use a boolean, obviously, bool turn ended. And don't forget to initialize your variables, folks. False. And return turn ended. And turn ended equals pin set all pins down. And that pretty much gives us our sort of basic implementation. If all pins are down, we're just going to return true on this. It's return ended to true, then it does this. So hopefully this should still pass the test without being completely useless. And it does, okay. So then let's say if we don't get a strike, then we can carry on. So scenario, not getting a strike on the first, string strike on the first roll results in not turn ended. And I'm just going to copy this, basically just modify it as we go, aren't I? So return, we pass on to all the pins. Let's just put the word not there. Not all the pins knocked down. So return false. Then we will turn it should be false. Require false. And that's our test. Make sure it fails. It should fail. And it passes. That's bad. We've clearly messed something up badly. Yeah, that's. Did it just compile? I'm starting to question if it. No, that didn't compile, mate. That's. Oh, it did. Okay, it did compile. All right. We have a legitimate bug. We require a call, so that's not failing. It returns false. and it indeed sets turn ended to be false. Because we generalize. This is the danger of generalizing. It is going to pass because this returns false, and then because all the pins aren't down, your turn is not ended. So you have to really think about that one. That's why maybe I should have done it in baby steps. But again, it's okay. I've analyzed it, and yeah, okay, this is fine. So we've kind of got our basic. We've got some very basic functionality in here now. It's able to take a pin set from you. It doesn't actually set a state yet. So what do we realistically want this to tell us in a given turn? Well, we probably need it to tell us the score. But again, as I was saying earlier, the concept of a score in 10-pin bowling is somewhat more complex. If you get a strike, that's not a score of 10. It's dependent on what you do next. So if you get another strike, you still have an indeterminate score. You can obviously get a perfect frame, and then it comes out to the maximum score, but you don't know what the player's going to do next. So this makes it slightly different. So we need to be able to discern this in some way. So one option, of course, is we could say that the player turn object doesn't need to know the rules of bowling. And in an individual turn, right, your score is somewhere between either 0 or 10, and it doesn't really need to know the game logic. So we can just have a simple score. So, but I don't think we should not necessarily call it a score. Let's call it pins knocked down instead. So we'll have a scenario having 3 pins knocked down results in a pins knocked down equals actually no, we need a final result, right? Because if I played one turn and in that turn I didn't knock them all down, I'm entitled to a second turn. And then what if, we probably shouldn't allow someone to disregard that. So we probably want to code a little bit of safety in, so that if later on we forget about it, it'll throw an exception and blow up, and we'll find out about it when we test that. So we're gonna design for that. But first of all, let's just have a basic score, right? We can build on it. So taking one turn. Actually, no, we will do it. It makes sense. So taking one turn without knocking down pins throws exception. Trying retrieving actually on calling get total. Okay, so it's fairly long-winded, but you get the idea. Given a default constructed instance of a player turn, and again a mock pin set, when we pass mock pin set with not all the pins knocked down, and let's just copy from here. So that's going to return false. Then get total should throw an STD logic error. I'm kind of more inclined to recommend throwing your own type of error that derives from std runtime error or std exception, but in this particular case, I think this is going to be this will be simple enough. You can throw a C++ built-in error. So we then want to call it and have it blow us up. So let's see, can we require, what can we require? Exception throw. Throws matches exception. Exception throws as, okay, that works. Turn dot, no, I think I have to put it in braces, don't I? Or do I? Just try it. Turn dot get total logic error. Okay, and let's just make that. So we will have our what's the magic max score you can get? It's obviously 10, so we'll just use uint last AT again. Get, what is it, score total? I've forgotten already. Get total const, and we'll just return nothing. Right, so that's not going to throw an exception, obviously. It's going to fail, hopefully. Let's see what happens. It does work. Yeah, no exception was thrown. We were supposed to throw an exception. So now we can obviously make it throw an exception. Date we need a return. Throw. First logic error. And fatal. Cannot get score until final turn taken. That'll work. Okay, so it should pass now. Seems to be compiling, yeah, much faster. Okay, so new scenario. Taking 2 turns without. Well, it doesn't matter whether you do it. Taking 2 turns does not throw an exception on calling get total. And we'll just copy this. And now I'm starting to question my design because I'm going to call this twice. And obviously, if I pass it, in reality I'm going to pass it as a real instance of some pins. But if I pass it a second time, well, actually it probably makes sense though from a term perspective, because I can pass it, I can probably reuse that instance and knock down more pins. So it's actually probably is reasonable. Because potentially, you know, if they don't knock down any pins, I can just pass it the same object, which is actually quite efficient. So I think that's actually okay. So we're going to call knockdown from pin set, and then we will just say require no throw start get total. And you'll notice that I'm not actually even bothering to check for a score yet. Not pins, turn, silly. Okay, and hopefully if I've understood how trompe-l'oeil works, this will fail. Yep. Fail due to unexpected exception with message, nothing. That's not very good. Why is it not printing the message? It's a bit of a shame. Okay, for some reason it's not printing that, but we can fix it anyway. So obviously our logic is that the turn we currently say the turn ends if all pins are down, right? That's not very great, because you can just keep on calling it. But I don't want to add too much code, so I need to sort of do the bare minimum now to make this pass. So what can I do here to make it pass? Well, I could set turn ended, but that's not going to work because I didn't set all the pins down. I called it twice. Obviously I need to count how many times this is called. That's the only way I can realistically do it. So we'll just have another uint. Or actually, do I even need to have a count? Because you have 2 turns, it starts in the false state, you call it 1. No, I didn't need a count, don't I? Let's have that then. Turns Maybe I should use an enum though. Might make more sense to use an enum. I could do that. So we can have literally have no turns, 1 turn or 2 turns. Those are the only valid states you're actually allowed. So strictly speaking, that's possibly the better way of doing it. Yeah, let's be type safe. We're gonna use an enum. It can be private. No one else needs to see it. So enum class turn state none 1 2. Right. Obviously, when we construct it, start none. So then, well, it feels more idiomatic if you had it incremented, though. That's the problem. I can sort of, but then I can't. This is sort of forcing me down the road of making it actually be consistent, though. So let's do that. So if that's not right. So if it's none, one, and I could actually represent this as a switch case, which I will refactor it to later. Not 2. That would not work, would it? See, would have broken the test right there. Okay. Obviously, we don't currently handle the state of getting past there. We should probably add an else just to make it safe. Again, this is one of those cases where you sort of have to think about what you're doing. You should probably write a test first. But I've been streaming for a while, so I'm going to power through it. All right. In fact, how long have we been streaming for? It's been all of, let's see, hour and 47 minutes. Right. Well, we'll go on for another 13 minutes, and then we'll finish there. I'll resume it later. Test taken 2, else throw stood logic error cannot take more than 2 turns. And yes, this could be a switch case. I'll probably do that later. And then turn ended is set to did you knock down the pins? That's not quite right though. So we actually need to generalize that. Actually, before we do, let's just take baby steps. So to make sure I haven't busted anything completely, let's run it again. This is as you're developing, just run your tests frequently. That way you know if you've messed anything up. So let's see what's failing. Failed due to unexpected exception, line 95. We've not picked that down, then it should not throw logic error. And it's still throwing an exception. So let's fix that then. Okay, so we're still failing. We haven't broken any existing tests. So get total obviously needs to well tell you how many there are. So if not turn ended, and throw that. Otherwise, we can just do turn. And now it gets interesting because I call knockdown from pin set in here, but I essentially don't even know what the score is. I literally have no way of knowing that. So the question is, how do we get the score? So within a given pin set, there's a number of pins that are down. So we can just use a simple number for that. So we've got turn ended, turns taken, and of course our current or pending total score. So we'll use that one, total score. I'll initialize that to 0. You could do equals 0. In fact, since it's a trivial type, we'll just use equals 0. And of course I need to then use that. So we set the turn ended and total score plus equals pin set dot pins down. We don't care how many are up, we care how many are down. That's your score. If you knock down all 10, then congratulations, you have won. Okay, so this now calls this. We're probably going to end up crashing, I suspect, because our mock doesn't do anything, but I'm not entirely sure what Trompeloid does when you call a function. Ooh, what's this? Apparently you can't actually compile. Oh, that's just a syntax error. What did I do? Oh yeah, didn't actually fill this in. Okay. So return, we'll just return total score, and then we can make it pass. Nope, I busted it. Okay, let's see what happened. Oh, we blew this right out, didn't we? So first failure is here. So all pins down. Yeah, we require a call. We call not have a pin set, but obviously we're not filling in the default there. So require call mock pins, and what was it called again? Pins down. So dot turn 10. And of course it's going to have to do that one. What's this one? Well, for this one, obviously it can't return 10. We'll say 0. There's none actually down. That's not indenting. Fine, be like that. And then this, of course, also need to call it. It should also return 0 because it's exclusive. And then our final test, they're not all down, so that can return 0 as well for now. We're not going to bother validating the score. You should just expect to do it now. What I'm wondering is, will it return that repeatedly? Let's find out. We're down to one failing test. So what are we busted now? That for an exception. Taking 2 turns is not for an exception. So we've got it once, twice, 3 times a lady, and it still throws an exception. So we have a bug still. So let's analyze what we've done here. So we call this. Sorry, no, we didn't call it. We called, what was it? Knocked down from pin set. We call it twice. So the turn state is initialized to none, and then we call it once, and it sets it to 1, and then it's going to check if the turn ended by checking if all the pins are down, and then it's going to come again, and it's going to set it to 2, and then it's going to check if all pins are down, and it doesn't care about the fact we're in the final state. So actually we just need to OR it with, in fact we should check our own field first because that's quicker. So turns taken equals turn state 2 or pins are down. And then hopefully if I've got my logic correct, it's going to actually successfully pass that test. Yep. Oh no, never mind, it doesn't. No, where did I break now? Why does it say line 105? That's weird. I'm slightly suspicious due to it saying line 105. That doesn't look like this line at all. Let's just comment this out and see if it still throws an exception, because maybe something's going on here that I'm not aware of. Yeah, something funky's going on there. We have a mock pin set. All pins down. Let's see if it's related to this. We're just going to comment this out, so we don't call the actual mock stuff. It's not going to do anything. It's for anyone to abort now instead, though. Yeah, it's going to abort instead, so we'll just ignore that. Okay, let's have a quick look at the old syntax on this. So require call in sequence times. Okay, so I think we need time. Okay, so return false. Dot times 2 times, and of course, it's going to do it twice. It's reasonable. Hopefully that'll solve our woes. I do think that Google Mock is. Oh dear. This is. I'm not a fan. I'm not sure I like this mocking library as much as Google Test. It's probably better in Linux. It's probably just me. But that's not a wonderful experience, sadly. Okay, so what we got wrong, and we are failing. Something's wrong. So we do expect this to be called time. All pins down, pins down. Not enough pin set. Maybe it's my code. Maybe I'm throwing an exception. Do I call it? No, I don't. If it's none, which it is, it becomes 1. So it's not going to throw there. That's the else statement. And then it's going to become 2, and you call it twice. That's fine. And we set turn ended. And then we set the total score. There's actually is there a bug in here still, because if I consider the turn ended, I shouldn't let you go on, really. Yeah. But anyway, so we call pins down twice. No, sorry, we don't. We call all pins down once, then we call pins down once. So we'll go around and we'll call it. There's no sequence on this. So the key question here is, why would it throw an exception? Get total. Now let's just run it again quickly. Do I ignore it and let it continue? No. It does not like me. All pins down is false. And then pins down 0 twice. And then equal this twice. Alright, let's just quickly comment this out, make sure I'm in the right place here. Go. And our survey says, yep, so this is the problem test to figure out what we're doing wrong. So we call get total. I suspect it's not. It's these that are busting it up though. So the mock pins takes a const ref, right? So we get a const ref to the type. This is obviously virtual dispatch. But hold on, this short circuits. So when we call this a second time, so we call it once, we take on 1 go, and then we call it again and we take it a go. We will not actually call this a second time. We'll only call it once because of my optimization. So this is a case where my test was right, but my actual implementation, my implementation was right, my test was not. So now we should find that hopefully this will do the job. And indeed it does. So you have to think about these things. Anyway, so we've done that. We now know that it doesn't throw an exception now, so that's cool. Let's have a look what we've got here though for the state. Well, what could go wrong? If I keep on calling it, it should throw an exception, so should we do that next? Although if I knock down all the pins, it should not let me call it again. So that would be an error, wouldn't it? So we can add a scenario for that. So we just want to expect this one. This one I can just copy and adjust. Actually, no, I'll do this one. That makes more sense. So knocking down all pins. Cause an exception, I'm calling get total. But only 1 flag. Actually, no, it's knocking down all pins on the first flag. Cause exception, go. Okay. So now we expect this to return true once. It should return 10, obviously. It's only once, so I'm going to simplify this. And we're going to call, actually no, not calling get total, calling Okay. Your pass mark will be set with a pin set, not my pin set, with all the pins knocked down. And then we're going to take that. Then should first a logic error. Right. So we call that a second time, put it once there. That should obviously fail, right? Well, more precisely, the test should not pass because I haven't implemented it yet. Oh good, it passed. Why would that pass? Maybe I did do it correctly. So let's see what's going to happen to think about this. Because again, if it is correct, that's fine. But you need to think about it. You should expect it to fail. Let's see. Knocked out from pin set. So we call it once. It's going to set turns taken to 1. And then it's going to set turn. No, no, that's not right. It shouldn't throw an exception. So my test is wrong. All pins down. Score of 10. And yet somehow that's throwing a logic error. What do we do here? Hold on. This is it's trompe-l'oeil throwing the exception. It's supposed to fail. And it's not failing because it's trompe-l'oeil. So we're going to call how many times are we going to do it? Dot times 2. No. This is a problem now. Trompe-l'oeil is throwing exceptions, and this is literally screwing up my test. Oi, that's not fun. Okay, so it's going to execute this essentially twice. No, it's not. It's going to execute that exactly once, and it's going to execute that exactly twice. This is not fun. That's not very nice. Not very good for testing, I'm afraid. So this is once, because once it gets the second go, it's done. This is going to return 10 once, but I'm going to fail. Alright, ladies and gents, I have the solution. I'm going to do what I said in the first place. Yeah, we're going to do it, right. Class, what should we call it? Turn state violation. And that is how you know, I'll just make it a struct. There's literally no point in doing that. Great, we've got our own type. And now I'm going to make it throw that right there. And the reason I'm doing that is because really I'm just trying to work around trompe-l'oeil, sadly. It is throwing something that's derived from that, which is a problem. Hopefully this will fail now because it can't downcast to this, it can't catch that, I hope. And then of course we're going to say throws as that, and where else do we do it? Throws as that, and I think that was the last one. Okay, so we've got a turn state violation, and that's going to do it twice. Actually no, should you do it once? No, should only do it once, because the second time we call it, it's already violated. It should not call them. So actually, let's just make it explicit. It should only do those ones, right? Come on. Can we just get a crash? At least if you have a crash, you know it's... Oh, Christ. No, here we go. That's good. That is good. Now we have an exception, but it's not the exception we expected, so that's a failure. So I can work with that. Cool. Okay. So we've violated our logic. We've violated our test because Chompaloy is doing this. I think I'm sort of turning towards trying to. I wonder if Google Mock plays well with catch. Probably not. Okay. So actually, I'm starting to run over time now. What did I say? Ooh, yeah. Okay. Fine. We'll round off in a sec. So let's fix this then. So we're going to go here, and of course our problem essentially is that if you have got a strike, so your turn has ended, then we need to throw the exception. And let's just quickly fix it and then refactor, and then I'll round it off. So if turns taken equals none, well then we're in the none state. That can't be a violation. Else, if turns taken is 1 and let's see, how do we know that we haven't violated it though? Not turn ended, because at this point it's going to be set to either we've done all our turns or pencil down. So if it's 1 and we haven't ended our turn, we didn't succeed, then so it's 2, otherwise lob the exception. So hopefully that should make it pass. It shouldn't break any existing code, any existing tests, and we should know that therefore we have a correct implementation. Excellent, we do. Okay. This kind of prevents me turning into a switch case, sadly. Well, it doesn't. It doesn't, but it's slightly more annoying. So I'm going to leave it as it is for now. In fact, we have our total score. So I think I'm going to round off here, and we can pick this up and develop more. I think next time, essentially, what we'll be doing is evolving this to return the actual score. Because if you look at the code right now, actually no, sorry, it does return the true score. So we'll hopefully add some. Do we have logic for that? Yeah, we don't even check the score. So I probably shouldn't have done that. Really, that was naughty. But well, we can reduce it to a return 0, and then build on it. But I think the next thing would obviously test that we would give the correct total score. Maybe add a bit more safety checking to it, of course. It can still take returns ended, and then essentially we kind of have our player turn class, pretty much done and dusted and designed. We know that it works because we've got all these tests that validate its behavior, and obviously there's not much code here, but there is a fair bit of logic required in order to ensure it's correct. And the beautiful thing of doing TDD here is that there were several bugs we encountered as we went through it, and we've caught all of them, and so you kind of have this internal feeling of being confident that it's actually working correctly. But anyway, that's the end of this stream. Hope you've enjoyed it, and thanks again to John for giving me the idea of doing this. I think it's gonna turn out to be a nice little sort of simulation. But yeah, cheers for now. And for those of you who attend our classes in person or online, we will be streaming the sessions as usual on Tuesday. But yeah, thanks again. Cheers and goodbye.